So good evening. Today we will start with the designing methods for the FIR filters. Okay. So there are four methods: Fourier series method without using window, Fourier series method using window, then Fourier transform method without using window, and lastly Fourier transform method using window. Okay. So this is a very good book if you want to understand how this designing method works, because I might not be having sufficient amount of time to make each and every examples understandable to you. So you can, at a later stage, you can go through this book and you can have a proper understanding. Okay. Now, frequency response of the digital filters, we have been discussing a lot about this. So just a recap, because understanding of this is important to design, to know how we can design the filters. Okay. So low pass filter in the analog domain, if you see 0 to omega c, we will be having a this pass band and then stop band. However, in the digital domain, it is 0 to omega c and then 2 pi minus omega c to 2 pi. Okay. So why this is so? This is because in the digital domain there is mirroring of the frequency response, okay, which we already discussed about. If you look over here in the z plane, so if you see, basically we are interested in 0 to pi, but if you look into the negative half of this frequency axis, 0 to or you can say 2 pi minus 2 pi to this 2 pi minus omega c, this region, we are having a mirroring effect, right? So mirror effect of the frequency components. So this is the important thing to remember. So whatever filter you will be designing, understanding the frequency response is of utmost importance. Okay. So this frequency response of the low pass filter can also be represented in this way. So minus pi to pi region. Okay. So in the previous one it was 0 to 2 pi, and in the second one it is minus pi to pi. So the total frequency region, it remains as 2 pi. Okay. Then in the case of high pass filter, we have something like this: omega c to infinity, you will be having a pass band, and lower than that you will not have the you will have the stop band. And if you look into the digital domain frequency response, it should be something like this: minus pi to minus omega c, and then omega c to pi. Okay. Then coming to the band digit filter, basically it is a combination of a low pass filter and a high pass filter. So if you look over here, so band digit 0 to omega c1, it will be the pass band, then omega c1 to omega c2, we will be having the stop band, and then we will be having again the pass band. Now this will be mirrored into the negative frequency components. Okay. So whenever you get something like this, you draw the frequency response in the positive frequency range, that means 0 to pi radians, and then you mirror it in the negative frequency region. Okay. So similarly, if you see the band pass filter, if you make the band pass filter, it should be in the positive region, it should be like this. So in the negative region, you will be having something like this. Okay. Now, how we can work or design the filter using the Fourier series method without using any type of window. Okay. In our next class, we will be basically discussing about how to use the window for designing the FIR filter, and what are the advantages of using the window, we will be discussing in the next class. Okay. So we will start with the low pass filter. Okay, we will discuss with the low pass filter, but the same method it applies to the high pass filter and other types of filter. Okay. So whenever you are given with to design any kind of filter, you have to first draw the frequency response in the digital domain, because we are designing digital filters. So you first draw the frequency response, then we have to calculate the impulse response Hn. Yesterday we have discussed what is impulse response and how we can get the impulse response, right? So as per the Fourier series method, the impulse response it can be given by h of n, which is equal to 1 by 2 pi integration of minus omega c to omega c h of omega e to the power j omega n d omega. Okay. Now, yesterday we have discussed that h of omega it is usually considered as 1. So it comes as 1 and our equation it changes to h of n equals to 1 by 2 pi integration of minus omega c to omega c e to the power j omega n d omega. Okay. So once you do this, because you will be getting this omega c components from your question. Now once you have got that, you have to solve this integral. You have to solve this integral. Okay. And once you solve this integral, then you have to find out the different impulse response values. Okay. Say for example, what is the length of the filter? Length of the filter is given by capital N plus 1. What is capital N? N is the order of the filter. Okay. So, in what regions your small n values should vary? Small n values should vary in the region of 0 to small n. 0 to small n. Okay. Now, suppose the order of the filter is 10, then your n value it will vary from 0 to 10. Now what is the length over here? If you consider 1 2 3 4 5 6 7 8 9 10, 10 plus the 0 component, so you get a length of 11. Okay, so you get the length of 11. So once you solve this equation, from the order value you have to put the change the value of small n and you have to calculate the impulse response. Okay, you have to calculate the impulse response. Now once you got the impulse response, we know how to compute Z transform. Okay, we have discussed yesterday also. So you compute the Z transform and lastly you have to realize the filter. Okay. Now the realization of the filter can be, I can tell you that you implement it in the cascade fashion, you implement it in the direct form method. So whatever method will be discussed, you have to implement that in that way. Now let's start with the designing of an ideal low pass filter. So in the ideal low pass filter, if you see capital HD e to the power j omega, which is the frequency response, okay, which is basically the frequency response. So if you see your y-axis is HD e to the power j omega, or in some books you may find it HD within bracket omega. Both are the same thing. Okay. Now it is given, since it is given over here, it is ideal low pass filter. So if you look into the response, it is given 1 in the region of 0 to pi by 2, and if you see over here, it is modulus of omega, right? So modulus of omega means in the region of 0 to pi by 2 in the positive half, and also 0 to minus pi by 2 in the negative half. We are having an amplitude response of 1. So if you see, we are having an amplitude response of 1, and outside this we have the stop band, right? Now we know this omega c values. Equation we have already discussed. HDN equals to 1 by 2 pi integral of minus pi by 2 to pi by 2 e to the power omega n d omega. Simple. If you do the integration of this one, 2 pi it will come. So this j omega or j omega n, no, omega is your variable. So omega n it will come in the denominator, and the same fraction it will come in the numerator, it will go j omega n, and you have this limits, right? So You break this limit, you get the this thing, and you take 2j within the bracket. Okay. So why we have done this? We have done this because if you see e to the power j theta minus of e to the power minus j theta, it is equal to 2j sine theta. It is basically 2j sine theta. Okay. So here if you see this fraction, it has now become sine theta. Okay, it has now become sine theta. So sine pi by 2 n divided by pi n, right? And this is the only integral what you need to solve. Just you have to put the limits. You don't have to remember longer integrals, especially for the FIR filters. Okay, so this is the only integration sum what you have to do. So just knock it up, right? Now the next thing is our length. It is given as 11. When the length is given as 11, capital N is equal to 10. Okay. So length is N, capital N is this thing. So we will compute HDN. It is equal to sine of pi by 2n divided by pi n for modulus of n less than equal to 5. Modulus of n less than equal to 5. So what we are saying, that our n value, it will vary from -5 to +5. Okay, and in other regions it would be 0. So how will you get this limit? It is nothing but modulus of n less than equal to n by 2. Okay, modulus of n less than equal to n by 2. So once you have got this, now if you put n equals to 0, so what happens? Sine pi by 2, sine of 0 divided by 0, infinite. Okay, so we cannot directly solve this one. The thing is that whenever you will be getting such kind of equation, component where both in the numerator and denominator you are getting zeros, you have to apply L'Hospital's rule. Okay, so you put HDN equals to limit of n tending to 0, and then you put this one. Okay, now what you do, there is a formula where it says limit of theta tending to 0, sine theta by theta is equal to 1. So if you see some, we are nearer to this thing, but we have to do some manipulation in the equation. Okay, what is the manipulation? You multiply the denominator with 2 and divided by 2. So this 2 comes out, so you get half, and then you get limit n tending to 0 sine theta by theta. So this becomes 1. So your HDN for n equals to 0, it becomes half. Okay. So 0 ka point you have got. Now the next thing is that we are having n values: 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, and 5 minus 5. Okay. Yesterday we have discussed that FIR filters, they have symmetric values. Okay, they have symmetric values. So you calculate only the values of 1, 2, 3, 4, 5. So you will be getting the same values for h of minus n, minus 1, minus 2, minus 3, minus 4, and minus 5. Okay. So if you look over here, n equals to 1, if you put, it would give us the result for HD1, HD minus of 1. You put the values, you get the results. And while putting it, make sure your calculator, it is in the radians. Okay. So many students, they do mistake, they put it into degree and then say sir हमारा तो result नहीं आया. So make sure, and it comes with practice. Practice नहीं करोगे, you will be a dead fish in the exam. So practice with your calculator, you get conversant with the calculator. Okay, so if you are not conversant with the calculator, you will face trouble in your examination. Okay, similarly, we'll be putting the n values. N equals to 2, we'll be getting hd 2, hd minus of 2, it is 0. Likewise, n equals to 3, n equals to 4, and n equals to 5, we will be getting the values. So see, for all the values we have got some values. Now the thing is that if you see the n value, it is moving in the range of minus n to plus n. Okay, that is again a disadvantage. Why? Because while realization, but we have, suppose, consider the case of hd of minus 1, so we will be having 0.32 multiplied by z to the power minus of minus 1 to z, right? So we don't have the operator for this one. So what we have to do, we have to shift this negative values to the positive values. How to do that? Just add 5 to these n values, and this is what we do using this equation. This is the generalized equation. Here we have to add 5 to the n values. Okay. In other cases, you will suppose if you are having 20 as the order of the filter, you will have to add 10. So for generalization, we need to use this one. So what it is z to the power minus of L minus 1 by 2. So in our case, z to the power minus 5, L was 11, minus 1, 10, by 2, 5. Okay, so we are multiplying it with z to the power minus 5, and then we are having the summation of n equals to 1 to L minus 1 by 2 h of n z to the power n plus z to the power minus n. Okay, so what we are doing basically, so basically if you give it as z to the power n 5 and then plus z to the power minus 5, so what we get basically, right? So what we have done, this what we are basically doing, we are pushing this n values on the positive n scale. Okay, so that is the thing. And when we are working with this one, we are having this h0. Okay, so h0, it would come as z to the power minus 5. Okay, so this is what it has been shown over here. We have put the limits, and then we have got this equation from there. Okay, so you have to again solve it, and after solving, you have to realize the filter. Similarly, coming to the ideal high pass filter, see, same equation you have been given. Okay, here length is again 11. So first we have to draw the amplitude response. Okay, so these are the limits we have come to know. Then we have to do the integration 1 by 2 pi. There are two regions, minus pi to minus pi by 4, and here pi by 4 to pi. So drawing this phase response or frequency response, it helps you in getting the limits. Okay, now again in the same way you do the thing, we get this HDN equation, same way you have to solve it. So for n equals to 0, you have to apply the L'Hospital's rule, you get the value. For the other things, you get the values, and then you will get the transfer function. Okay, and then you can realize the filter. Similarly, design an ideal band pass filter. Again, see, limits are given. You draw the frequency response, you will get the limits. Once you get the limits, HDN, say the same integration we are doing, solve it. Okay, so after you have solved this one and you have got the HDN, then calculate the values, and after you calculate the values, you calculate the or compute the transfer function. Okay, now previously we have been discussing about the phase responses. By the placement of the poles and the zeros and by computing the distances, we are able to get the amplitude response, and by computing the phases we could have got the phase responses. We did not go into that because it was a more tedious job. Now in this case, if you are given with something, how will you find out the phase response or the amplitude response together? Okay, the thing is that suppose you have got this transfer function. Now in this transfer function, for a frequency response or the amplitude response, where we are interested with, we are interested on the frequency axis. And where is the frequency axis? Frequency axis is your e to the power j omega. So replace your z with e to the power j omega. Okay, so 0.5 multiplied by e to the power minus j omega 5 plus, again for these terms you put z, replace z with e to the power j omega. So you will get this type of equation. Now again, this type of equation, it can be broken down using this equation, e to the power j omega equals to cos omega plus j sin omega. Okay, so you break it down, so you will be getting the stuff in this fashion. Again, now in each components you see there are some real components, some imaginary components. So bring the real components together and get the imaginary components together and then solve it. And once you solve it, you will get it in this form, a plus jb, and from there you have to find out modulus of h of omega, which is equal to under root of a square plus b square, and phase of h of omega is tan inverse of b by b. Okay, so now for the phase, for the amplitude response, you change the values of omega, say 0 radians. Okay, you put the values and you will get the answers. Similarly, for the phase response, you put the values and you'll be getting the results. Okay, then you make a table: 0, pi by 4, pi by 2, 3 pi by 4, and pi, and putting the values. Okay, so in low pass filter there might be another type of question, or even in the high pass filters also. Instead of uh, directly giving the, what you call, this cutoff frequency in radians, you get it in the form of hertz. Okay, you get it in the form of hertz. So how do you find out this or convert these uh, frequencies into the radians? The frequency is the we call it the normalization process. So the normalization process is omega c equals to 2 pi fc by fs. Okay, fc by fs. So fs is your sampling frequency. So 2 pi 500 by 2000 equals to pi by 2. Okay, now once you look into this, basically it is the same equation what we have discussed in the first case of low pass filter, and the rest of the processes it remains the same. Suppose you get it for the high pass filter, again you have to convert it into omega c equals to 2 pi by fc by fs, and then you have to do the thing. Okay, so now I would like to ask you to practice these questions, and if you find any difficulties then we can discuss.